There we go. Okay, I imagine you guys have some questions on the homework?
88,
88.
please.
We have it too. In a steam heating system, air is heated by being passed over some tubes through which steam flows steadily. Steam enters the heat exchanger at 30 psia at 400 degrees Fahrenheit at a rate of 15 pound mass per minute and leaves at 25 psia at 212 degrees Fahrenheit. The air enters at 14.7 psi and 80 degrees Fahrenheit and leaves at 30 degrees Fahrenheit. Determine the volume flow rate of the air at the inlet. Okay, so how did you start?
Well, I got an energy balance.
That's good.
Energy in equals energy out.
Okay, I agree.
Um,
How does energy flow into and out of the system?
Well, it's got energy from the air and energy from the steam going to the heat exchanger.
In other words, the mass of the air carries energy with it, and the mass of the steam carries energy. What kinds of energy do those masses carry?
Flow energy and thermal energy.
Those are the two big ones, aren't they? Okay, now is there any significant flow energy change in the air, do you think? Remember, the flow energy is the PV term. Now, the pressure is constant throughout that, and the air probably doesn't change volume a whole lot. As a matter of fact, remember that, well, we'll go ahead and use enthalpy, but it probably wouldn't be a big difference to use in terms of energy, because the temperature change of the air is not all that big. It's only 50 degrees Fahrenheit. So anyway, what that means is the volume won't change, the density won't change by a whole lot. But anyway, let's go ahead and sketch this thing so we can solve it and look at it. Basically, this is just a heat exchanger problem where you've got air flowing in and steam flowing in. I'll draw it as if it's a counter current heat exchanger, but it's probably a cross flow heat exchanger being a home heating application. Air, we know, comes in at 80 degrees Fahrenheit, but leaves us at a nice comfortable 130 degrees Fahrenheit. Now, you guys know I have a boiler system at home that uses hot water to heat my house. It doesn't work this way. It doesn't generate steam, it just generates hot water. And then the hot water is used. The hot water in my house only goes up to, from the boiler, only goes up to at most 200 degrees. Most of the time it's around 170, 180, something like that. So this is a lot hotter. Let's see, what else does it say? We've got a mass flow rate of the steam that is 15 pound mass per minute. Maybe one of the reasons you couldn't read the handwriting on the video is the handwriting itself, not the video. Try to do well, but not doing too good right now. Okay, lead is at 25 psia. That's the steam, yeah, and 212 degrees Fahrenheit. And what else? I think that's everything for the air. No, we've got a 30 psi a pressure coming in. Why would the steam come in at 30 psi and leave at 25? Why does the steam come in at 30 and lose at 25?
Losing energy.
Now, wait a second. The steam, the heat exchanger is essentially a pipe. It's an open pipe that connects one side to the other. So why would it lose any pressure?
Because it's changing temperature. It's
But-
giving energy over to the air.
It's also
Okay,
because
wait a
it
second.
gets condensed.
Okay, well, wait just a second. The pressure of the air is 14.7 psia. What do you think the pressure of the air is coming out? 14.7 psia. Why? This is just atmospheric pressure, right? Okay. In other words, basically there's a big duct in your house that this air flows through, and that duct is just open, so there's no way that the pressure can change significantly. Now, in a home heating duct that carries either air conditioning or conditioned air, as they call it, it is possible to have some pressure loss along the ductwork, but it's not much. In fact, if you want to measure it, you have to use a water manometer. measure it, or electronic instrument that's as sensitive as a water barometer. So, anyway, it's a very small pressure drop. Now, this steam has some pressure drop. Now, you guys said the reason it had that pressure drop is because it's temperature change. I disagree. I think the reason for that pressure drop is probably because this pipe is not quite as open as it could be. Maybe the velocity is high enough, the frictional effects of viscosity of the steam make a difference, I don't know. But basically, all this is a little bit of pressure drop across the heat exchanger. Now, real heat exchangers typically have a little bit higher pressure drop. And I've told you guys many times about my home heating system, but I'll mention this one thing. I did something kind of interesting. I bought a heat pump, found one on Craigslist with a 5-ton heat pump, and ended up paying about a third of what I should have paid for the whole thing. Put it in my basement. It was a vertical flow system, so I designed up a couple of brackets. I just basically screwed some wood onto the side, designed up a bracket, and mounted it to the wall. That way it was up off the floor because the air enters on the bottom. That made it really nice because then what I could do, and even though it was the wrong place, I really wanted to put my heat exchanger on top, but I couldn't. I had to put it on the bottom. So I put a cross-flow heat exchanger where my boiler sends in the hot water. So basically hot water comes in one side and moves out the other. It's just pipes. Now, when I selected this heat exchanger, I knew that air would have to flow through it. Now, there's already an A coil inside of this unit. Okay? And that A coil has refrigerant that runs through it. That refrigerant either operates in heating mode during the cold weather, right, for the heat pump, or in cooling mode as an air conditioner during the summer. Now, during the summer, of course, I'm not going to turn on this coil. But in the wintertime, I turn it on, and in any case, this coil is always mounted here. And so what's kind of interesting about this, relevant to our problem, is the fact that this is called a low DP coil. You don't have to write that down or anything. What that means is it's a low differential pressure coil. In other words, if you look at it, it's a lot more open than most of the heat exchangers. If you look at that one back there, you'll notice you can't really see through it, when you look straight on at it. But if you look through mine, you can see through it much better because it's still pretty thick to make up for that fact. It still has a lot of heat transfer surface area, but the air pressure does not drop very much because they know that people are going to add this to a system where there's already a bunch of other things in the way. Anyway, so there can be a pressure drop on the air side as well, but in our problem here, they apparently haven't given us that. Okay. So you wrote, I'm sorry.
The Shepherd project is saying that there's a problem. Is that
What is it?
Yeah, it's not a homework problem.
88 isn't a problem, Shepherd thought.
81.
81.
Oh, crap. Well,
It's a sin of I guess.
guess I did the wrong one.
I'm going to go ahead and solve it because it's an interesting problem. It won't take us very long to do it. But basically, all I'm going to do is make a control volume here. Well, this is the same kind of thing that's going to be on the exam, so we may as well see it, right? So you're right, the air carries energy in with it, the steam carries energy in with it, the steam carries energy out, and the air carries energy out. So what do we have to do? Well, we have to quantify all those flows. So basically, the mass flow rate of the air times the enthalpy of the air coming in. Let's give these some state numbers. Let's make this 1, we'll make this one 2, this can be 3, and this one can be 4. And now I can talk reasonably about this. Where the air comes in, I'll have the enthalpy of the air coming in. Where the air leaves, I'll have the mass flow rate of the air multiplied by the enthalpy of the air as it leaves. Okay, so notice this is a deposit of energy within the control volume. This is a withdrawal of energy. There's another deposit from steam, so the mass flow rate of the steam multiplied by the enthalpy that it comes in with, and then less the mass flow rate of the steam times the enthalpy that it leaves with. Anyway, all these taken together equals 0 because all these deposits and withdrawals into our little system bank here equals 0. However much in comes in, flows out. Now you might remember that we solved this before. I had a solution for you in the slides. It says that the mass flow rate of the air equals the mass flow rate of the steam. Let me think for just a minute. If I move the mass flow rate of the steam to the other side, H4 and H3 will flip signs, so this will be H4 less H3. And then if I factor out H1 and H2, then they would end up in the denominator as they are. Well, this is the equation that we got from the slides. Okay? It's just an energy balance. Now, H3 and H4 are associated with the steam. How do you think I'm going to find H3 and H4?
Back to
Go back to the book and look it up. How about the enthalpy change of the air? CP delta T, that's right. So we're gonna use m dot steam multiplied by the heat capacity of the, what is it? I'm sorry, it's on place. H4 less H3, because that's the steam, 3 and 4 is steam, over CP T, let's see, we'll want T1 less T2.
Why is it not T2 less T? Okay.
That's
T1
H1 less H2, so I have to do that.
Two's one in there, okay.
All right, let's see, so why don't we go look up some properties? If we look at 30 PSIA and 400 degrees Fahrenheit steam, what do we find? My guess is at 30 PSIA, that's gonna be superheated. Water boils at 212, when you're at 14.7, roughly half that, about 15 PSIA. Your 30 PSI is probably not enough to keep 400 degree Fahrenheit water from boiling off.
Yes, we have to do that calculation, because there's no, 30 PSI, though.
What do they have? What do they have?
20 and 40.
20 and 40? Let's make our lives easier and let's make this 40 PSI. How's that? Sound good? So what's the enthalpy of state 3 then?
At 400 degrees,
1236.5. PT per max.
Yeah. Thank you. Then how about 212 degrees, 25 PSIA? Would it be superheated there too or not? Wait a second. 25 PSIA, let's think about this. That's a little bit more than atmospheric pressure, so yeah, it wouldn't be superheated, you're right. So let's go and look in the set. And how did I know that? Because at 212 degrees Fahrenheit, the pressure would have to be about 14.7 for pressure is too high. Okay. So let's go and look that up in the saturated tables. Do they have either 212 in the temperature table or maybe 25 PSIA in the saturated table?
25 psi.
In other words, so tell me the enthalpy of saturated liquid and the enthalpy of saturated vapor.
The saturated liquid is 208.52, and the vapor is 1160.6.
That's just at that pressure, not at the temperature.
Okay, so what is the,
Got that correction formula.
right, so what we're gonna do then, let's see, since we have a subcooled liquid, what we'll have to do is base our properties instead of on 25 PSIA, we have to base it on 212 degrees. Let's try that instead, so let's go to the temperature table.
181.2.
And what's that, HF?
Yes, saturated liquid.
And how about HG?
1150.
Well, we don't really, no, we do, yeah, I'm sorry.
It's 1150.7.
50.7, both these are BTUs per pound mass.
Yeah, that's not what I got.
I got 180.2 and 1150.3.
80.2, 11.3.
Oh,
You're still in the pressures, go, our other page, and go to 12 degrees.
okay.
Thank you.
I was looking at 212.9. It's still close.
So am I.
All right, so here we are. We've got HF and HG. Now, what are we going to do with all this stuff? Well, remember that the initial approximation for the enthalpy of a compressed liquid, I don't remember how we nomenclature we use. I can't think of it. Basically, it's HF at the given temperature plus a specific volume at the given temperature. It's it is actually HF. At the given temperature, multiplied by the pressure less the saturation pressure at the given temperature. So we need some other properties besides the ones we looked up. We got HF, we needed it, that's good. But we also need the specific volume of saturated liquid, and we need to know what the saturation pressure is at 212 degrees Fahrenheit. I can say that was 14.7, right?
Specific volume is 0.0167.
1671?
0.167.
Right. Cubic feet per pound mass. Okay, so now we can come up with an estimate for the enthalpy at the pressure and temperature that we're given. So HF is 180.2 BTUs per pound mass. The specific volume, VF, is 0.01671 cubic feet per pound mass. The pressure, well, what is the pressure? Well, the actual pressure is 25 psi. So that's what we need to put in first. The saturation pressure is 14.7. And again, let's calculate the magnitude of these two terms. I mean, you can already see this one, right? 180.2. What's the magnitude of this term? How much is that correction? 25 less 14.7, roughly 10 or so times this. It's about 0.16, right? So it's small. So this is going to come out to about 180.4 BTUs. No, wait a second. Let's remember units. I have to perform some unit conversions here. We've got cubic feet PSI per pound mass. I need a conversion factor to get me from PSI cubic feet to BTUs, and I think the number is 5.4 something. I think it's 1 BTU per 5.4, help me out here, PSIA cubic feet.
Yep, 5.40395 PSI per cubic foot.
5.4 what?
0395.
0395. Okay. So that's going to make it even worse, right? Because that 0.16 that we had divided by 5 essentially is going to make it even smaller. So anyone that's typed it into your calculator, what we have. Keep looking over here because I forget this is not the classroom.
So that's a generalized correction formula that you use.
Yes, that's right. It's a little more accurate. So if we take 25 less 14.7 times 0.01671 divided by 5.40, however many digits you want.
Is that in the book, that correction formula?
Back to the book.
It's not only in the back of the book, it's in the chapter where we discovered it. In fact, I think it's in the back of the chapter. Let's see, I think it's the end of chapter 3, if I recall correctly. Find out. No, let's try chapter 4. It's buried in the chapter somewhere, but I don't remember what chapter it's buried in. I know I've seen it in there.
Chapter 4, you said?
I think it is chapter 4.
Yeah, he doesn't have it in the summary part of it.
Yeah. It is in red though, as I recall.
Yeah, because I remember you told us to write it in the summary part of it at one point.
Yeah.
So.
It's handy to have. Sorry, I don't see it now. You want to have a number for me? 123? Yeah. So there's not much of a correction factor here. It's still BTUs per pound mass. Now, one thing I like to do, and I need to not forget to do this, how many of you guys have been on a power plant tour with
That's
us
what
before?
he just substituted.
Any of you gone? Which one did you go to?
Yeah.
Do the hydroelectric
Hydroelectric.
That's
I
what
usually
she
take
was-
the 220 class to the hydroelectric power plant on the river. But what I'd like to do this semester is take you guys to the coal-fired power plant. In the past, we've gone and visited the Cane Run Road power plant. They recently changed over to a combined cycle, which would be really fun to see. But I know how it goes when you change things, and you're still getting used to it. I don't want to bother them right now. So we always ended up going over to Louisville, but this year what I'd like to do is for us to go to a Duke power plant. So I'm gonna try to make some contacts at Duke. There's one down the river, not too far away, so we can go there and see how things work. To me, it makes this topic come alive, because you see that, hey, this is real stuff that's really going on. This is what a real turbine and boiler looks like. We can make it work.
Power plant, I want to find the representative.
Okay, thank you, appreciate it. It's just, I'll find out what it is, but it's the one on the river going towards, what is that, Elizabeth, Indiana?
If you would real quick, can you just, relate the universal one of that to what you wrote on there? 'Cause I'm kinda-
What do you mean?
Like the universal, like what you replaced, like obviously you replaced your Y as enthalpy, right?
You're thinking of this, you're
Am I
thinking,
thinking the wrong one?
yeah, you're thinking of the wrong one. You're thinking of this, Y.
Yeah, that's what
plus
I'm thinking.
X, Y,
Which one?
FG. These two are totally different things.
Okay.
This is more of a delta H equals, V delta P for an incompressible.
Okay.
Okay, for an incompressible
Well, I was
system.
just about to thank you for helping me, but never mind.
Thank you for helping, I mean, confusing.
Wait a minute, if not, I wanna see what you just erased.
Oh, sorry.
Because I'm trying to write it down.
It came from this, delta H equals, you probably shouldn't write this down because you'll think it's true all the time. This is only true for an incompressible substance.
Example,
Yeah, all right, liquid or salt.
that's in chapter, well, it's almost like that, chapter 4.
Yeah, it's in chapter 4, that's where we discovered it. This equation, this improvement on the estimation of the enthalpy of a subcooled liquid, that is somewhere buried in chapter 4.
So,
So that's only
can I
good
write
to
that down? I wanna write.
Yeah,
something.
write that one down. That one's worth having in the back of your chapter.
So that's only, it's only good though for press.
That's only for compressed liquid, something that's subcooled.
Enthalpy of a pressure and a temperature.
Well, it's the enthalpy as a function of pressure and temperature.
So if you have a pressure and temperature defined, that's how you find it, if you don't have it.
Exactly, right. It's subcooled. Now, we do have a chart of subcooled liquid properties in the back of the book, but they're not very extensive. Well, I say it's useful, but look, it doesn't really make that much difference.
Oh, yeah.
You know, most of the time I just grab HF and I'm done with it.
In the calculator, we calculated that at 81.14.
81, 181? I think.
Oh, I didn't do, I multiplied it.
Yeah. Okay, anyway, let's finish off our problem. Finally, we've got the enthalpy of the steam coming out. And notice it's coming out as a subcooled liquid. So its enthalpy is, we've got it right here, 180.23 BTUs per pound mass. Notice what's nice about this. It's obvious that the steam has gone through a phase change, but that makes absolutely no difference. Basically, the steam had a certain amount of energy here, has a different amount of energy here. This difference accounts for the phase change of the steam. So we don't have to worry about all those details. They just don't matter. They're already accounted for. So the mass flow rate of the steam was 15 pound mass per minute. The enthalpy at state 4, see that's where it's coming out here, is 180.23. The enthalpy coming in from the steam was 1,236.5. These are BTUs per pound mass. And for air, I'm going to end up with BTUs per pound mass as well, so I'm not going to bother writing down the units. The heat capacity of air, does anybody know the heat capacity of air right off? How much?
0.24 BTU.
0.24?
Pound mass.
4 BTUs per pound mass per Rankine. All right, I guess I'll go ahead and put it up here to show that they cancel. Okay, anyway, the temperature change T1, let's see, is, over there it's 80 degrees, and T2 is 130. Do we have a problem here since we've got Rankine there and degrees Fahrenheit there?
Change, so.
Change, it doesn't matter. BTU's per pound mass go away. And now we can figure out how many pounds mass of air is gonna flow through this thing. Guess we can calculate it all. You think it's more pounds of air than pounds of steam or not?
After all, air is pretty light, right? What do you think?
You should have a good idea. The steam went from a superheated steam to a subcooled liquid. It gave off a lot of energy. Okay? Typically, water can hold more energy per temperature change than air can. So I think that we're gonna have a whole lot more pounds of air going through this thing than we have pounds of steam going through it.
Water is a very substance.
I'm sorry?
Water is a very substance.
Water is an excellent substance. I'm glad it exists.
13,
Well, we
20,
wouldn't. How much? 1320.343, let's just drop that part. And that's pounds mass per minute. Anyone second that?
Yeah.
So see, it's not even close to the 15 pounds per minute of steam, it's a lot more. It's almost 100 times more. All right, so there's the mass flow. Now, what they really wanted though was the volume flow rate of the air, and they wanted the volume flow rate of the air right here coming in. Okay, well, we've got the mass flow rate of the air. How does the mass flow rate of the air relate to the volume flow rate of the air? Do you remember?
Density.
By the density.
Area.
You really don't need area, because look,
Density
mass
times
flow
volume.
rate is density times volume flow rate, because density times volume gives you mass. So, do you remember the trick that I showed you guys for coming up with density from the ideal gas law? I'll show it to you. PV equals RT. V is just the inverse of its density.
so it's just RT.
It's P over
Or
RT.
P over RT.
P over RT. You got it. Okay. So, what does that mean? Well, if we want V dot at 1, then we better take the mass flow rate, which is the same at 1 as it is at 2, but it's the mass flow rate of the air multiplied by RT over P, where we're going to use the temperature and pressure as state 1. Because we want the volume flow rate to stay. So let's see, the mass flow rate of the air we just found, 1320 pounds mass per minute. This is a lot bigger flow rate than your home heating device uses, by the way. Okay. Times the gas constant of air. Anyone have that one memorized in English?
But, just a page turn away. Air's gas constant in English units is 0.3704.
0.3704, and that would be PSIA
PSI times
cubic feet per pound mass per Rankine, right? Okay. Let's get rid of some of this. We can remember that we've got 14.7 PSI and 80 degrees. That's not a big deal. So let's see. Let's see, the pressure. I guess I don't need to put it there. It doesn't matter. Pressure is 14.7 PSIA. And the temperature is 80 degrees Fahrenheit. I can't catch you guys anymore. I can't put my mouth straight. It doesn't work. I start laughing. You know I've done something wrong, right? What have I done wrong? Rankine. So now we've got Rankine. How come the degrees Fahrenheit didn't cancel off this time? How come I had to add?
It wasn't changed this time.
It wasn't changed this time. That's right. It was a total temperature. So you guys are learning a lot. Pound mass go away. We get cubic feet.
Learn which homework problems we get to do.
Well, hopefully this will help you on the exam.
Maybe you
Y'all
can
be on
talk,
81.
maybe you can,
I'll be glad to help you.
maybe you can talk to me.
No, it did.
Maybe
Oh,
like,
it did.
yeah, switching out, probably do that,
Do I have to do 81, because I already did the wrong one?
Once you get enough practice, I don't care. Okay, we have a number here for the volume flow rate. Everybody? $2,960.6 to 961, and that is cubic feet per minute. Yeah, cubic feet. Pretty good flow rate. All right. Let's see. I think, Mr. Blackman, you were in my office earlier asking for help on a few problems. Do you still need help on any of them?
123.
One point.
That's possibly skipping a dive.
What's that?
Possibly skipping a dive in front of everyone else.
123. An insulated vertical piston cylinder device. Well, you almost have this one worked out. You want to come up and write down what you got? It's fine. You don't have to. Just so you don't want to show off.
Show off my mad analysis skills.
That's right. Okay. All right, insulated vertical piston cylinder device. Draw it. This one has an inlet. Because we've got steam coming in on the side. Comes through a valve so that we can shut it off if we want to. Incoming pressure of the steam is a 0.5 megapascal, or in other words, 500 kilopascals. Let's just put it in that way. Temperature coming in is 350 degrees Celsius. The pressure in the piston cylinder device is apparently 200 kilopascals. The mass, the total mass, which it doesn't matter if it's state 1 or state 2, it's going to stay constant. Well, no, it's not. It doesn't matter. I'm sorry. This is an unsteady problem. We're adding mass. So the mass in state 1 is 10 kilograms. And this is water. And I start off with some liquid water in there, apparently. In fact, 6 kilograms of the mass, let's see, how shall I say this? In state 1, the mass of the gas is 6 kilograms. So you tell me, what's the mass in state 1 of the liquid? 4. Okay, what else? The mass of the piston is such that it maintains pressure, steam at 0.5 megapascals, 350 comes in, until all the liquid in the cylinder has evaporated. Now that's important. All the liquid in the cylinder has just evaporated. What does that tell you about the state of the system in state 2? It's all vapor, that's true, but we stop right when the last droplet of water evaporated. Saturated, that's right. So state 2, the quality in state 2 is 1.0. That's really important. Now, when you're solving unsteady problems like this, you need two things all the time. You need a mass balance and an energy balance. Maybe even some luck in the third one. Okay? So, let's work on this one. The energy balance, let's start there since that's the, well, actually, let's do the mass balance since that's an easy one. Mass balance. You understand that we started with 10 kilograms, but we're going to end up with more in state 2? In fact, the mass in state 2 must be greater than the mass in state 1 because we're adding mass to the system. This is simple, right? So mass in state 2 equals the mass in state 1 plus the mass that comes in. Let me put a note down here. We don't know how much mass comes in yet, but we'd like to find out. We'd also like to find out the temperature in state 2 because that's something they asked for. Now wait a second. What's the pressure in state 2? same, this is the cylinder device. Pressure is still 200 kilopascals. Well, if the pressure is 200 kilopascals and the quality is 100%, what does that tell you about the temperature in the station? Still in the saturation region, so it must be the saturated temperature. Right? So we can figure out the temperature in state 2 pretty easily. It's just Tsat at P2. So all we have to do is look it up. So look up the saturation pressure of 200 kilopascals. I know what the temperature is. 120.2 degrees Celsius. Good. Got to take care of the easy things first when you're solving these problems, and the rest of the pieces fall into place. So there's the mass balance. It hasn't really done much for us yet, but there it is. Let's write down the energy balance next. 23, I'll move that out of the way. The energy balance is probably the most important one, but before we write it down, let's figure out what it means in words rather than in math. What happens to this system energy-wise? Are we making any deposits of energy? Where? Through the valve, right? We've got mass carrying energy in. I agree. What kind of energy does it carry? Carries thermal energy. What else? Those two together are enthalpy. So we're probably interested in the enthalpy of the incoming stream. Why don't we go look that up while we're at it? So look up 500 kilopascals and 350 degrees Celsius. Let's go straight to the superheated tables because that's where you'll find it. 3168.1 kilojoules per kilogram. Everybody see where that came from? There's our process going from state 1 to state 2. Now let me ask you this. Is there any heat transfer here? Q dot or Q?
What is it, 500, I'm still trying to look this up. What is it, 500?
Yeah, here we go. 500 kilopascals, 350 degrees Celsius.
And I'm looking for the enthalpy.
So look at the parentheses, yes.
3168.
Yep, 3168.
It doesn't say.
Well, I'll give you a big hint here. You ready for the big hint? We boiled off some water. So was there any heat transfer? How do you boil water on your stove? What do you do?
Transferring it into it.
Okay, so how do you boil water here? No. Push it into a hole. You change the pressure, the pressure staying constant. What do we do? We put mass in that has a whole lot of extra energy. This mass that's coming in is superheated. In other words, it's way above what it really needs before it even gets close to condensing out.
So it just adds it to the system.
The effect is that it boils off some of that water. So we add a little bit of this mass and it boils off quite a bit of water. Okay? Eventually it's going to come down to M sub G, or V sub G. H U sub G. I'll get it right eventually.
Just say all the letters.
All of them. Now, why was I going back and forth? Why did I say H sub G and then correct myself? Because this can't have enthalpy. Neither one of these can have enthalpy. They can only have internal energy. Okay, so eventually the energy of the gas as it comes in is going to wind up at U sub G. Okay?
There's a reason they can't have enthalpy because they don't have flow energy.
They don't have any flow energy, that's right. Even though there's some pressure and specific volume, that is not a measure of the energy of the fluid in the container. All right, so we've just figured out that we're depositing energy, and we figured out that the energy in the system is going to change. Because we're going to boil off this liquid, it's all going to become a vapor. So apparently the amount of energy in the system changes due to the phase change, but also due to the fact that we've got more mass in the system in state 2 than we had in state 1. So the system energy increased because we literally carried energy in that stayed in, right? Some of the energy came in and it boiled off some water, but some of it came in and just added to the energy in the system. There's more than 10 kilograms of mass in the system now. What about withdrawals? Any withdrawals? I would definitely count boundary work. Absolutely. There's definitely boundary work leaving this system. You can't neglect that. So let's write down the energy balance. Basically, it says deposits less withdrawals equals the change in the energy of the system. We have to be careful though and make sure we get it right. The amount of mass that comes in times the enthalpy that comes in would quantify the amount of energy carried in by all the mass. I don't know how much mass there is in this thing yet. We'll figure that out later. That's one of the reasons for writing down this balance. So it's a good thing that we have that unknown in the equation because we need to find it. It's also here, so we haven't added an unknown yet. And so the mass of the incoming stream times the enthalpy it carries tells us exactly how much energy that stream is carrying in. Withdrawals, the boundary work. You subtract off all the energy that leaves via boundary work. Are there any other deposits or withdrawals? How about the water that boils off here? Is that a deposit or a withdrawal?
It's within the system.
Within the system, so it's a change in the account balance, right? So this is all. Those are all the deposits and withdrawals. And what happens? Well, the system goes from state 1 to state 2. You always have to take final minus initial. In other words, if you want to calculate, let's say you deposit $10 in your bank account, and you know you started off with $100 in your bank account, and you want to calculate the change in your bank account, and you didn't want to use the $10 to do it, your final account balance would be $110. You'd have to subtract off the additional $100. That would be a $10 change. You always take final minus initial. Same thing here. So the mass of the system in state 2, now what kind of energy did the mass in the system hold? Internal, or essentially thermal energy, right? How about in state 1? Well, same thing, but a different amount, right? So there's our energy balance. Now, why did I put M2 and M1 here, and U2 and U1? Can we combine those somehow? We usually did before.
There's a change, they're all
You
changed.
one is,
They change it.
That's right. U1 and U2 are different, M1 and M2 are different, so we can't just combine them like we've done before. Okay? All right, well, things are, pardon?
I was gonna say, we know the mass and state one already, and we also know we can get the internal energy, right?
The internal energy in state 1 and state 2, I think we can get those two things. That's not too bad. In fact, over here, since we know all this stuff, we could probably just look up U2. It would be U sub G at 200 kilopascals. So go ahead and read it off. We'll write it down.
What, temperature?
Just look up pressure, 200 kilopascals. That is saturated. 120.2 degrees Celsius, if you want to look it up. Same line.
UG is 29.1.
9.1, and this would be kilojoules per kilogram, right? Okay. Could we get U1? I checked it off.
Sure.
Remember the equation you asked me about earlier? U1, average, is equal to UF plus X, let's put ones on all these, U, G. So how are we gonna find out all the U properties? Well, what we'll have to do is go and look up, it's like saturation pressure at 200. So we've already got one of the pieces we need. We've got UG, but we need UF. So what is UF?
504.5.
How much?
504.5.
What is the quality in state 1?
0.6.
0.6, it's 60%, right? Because we've got 6 kilograms of gas for a total of 10 kilograms of mass. 6/10 is 0.6. So X1 is 0.6. We should probably write that down over here. This tells us that X1 is 60%. And now we need UFG, so we just need the difference between UG, which is the same as it is in state 2. 25, 29.
20.4.6.
Oh, it gives you 24.
It gives you UFG.
Okay, what is it again?
20.4.6.
124.6 kilojoules per kilogram. That's good. Some of the stuff we don't need anymore from the last problem. All right. So now plug all that in your calculators, and we'll come up with the internal energy in state one. See frowns, what's wrong?
I stepped out, I'm okay, I believe. I was looking at your energy balance,
Yeah, well, here's a deposit,
yeah.
here's a
And
withdrawal,
You got your boundary work,
all right, that's a withdrawal.
and that's gonna be equal to,
We'll figure that out in a minute, we haven't
yeah,
figured it out. But, oh, these two together, yeah, that's gonna be equal to the change in the account balance, basically the amount of energy right in here.
yeah.
So that's M2U2 final, M1U1 initial. Right now, we're just working on all the pieces.
17, 19.36.
19.36 kilojoules per kilogram. Okay. So there's U1. Let's bring it over here so we can have it when we need it. 17, 19.36 kilojoules per kilogram. All right, now we've got the mass in state one. Let's see, what's unknown? The mass in state two, the incoming mass. Those two are two unknowns. The enthalpy of the incoming stream, we already know, we looked that up earlier. We probably better figure out the boundary work. How could we figure out the boundary work? What do you think?
Constant pressure.
Pressure, good, so boundary work is equal to P delta V. So that's gonna be P, V2, plus V1. Right? How are we going to get the volume in state two and the volume in state one? Volume in state one is pretty straightforward, right? We'll have to do something like this again. V1 equals VF1 plus X1 VFG in state one. So we're still living on that 200 kilopascal line. We're wearing it out of the book, but we can get that. So we could write this as P times M2 V2 less M1 V1. Right. So let's go ahead and calculate the specific volume in state one. We may as well get that out of the way while we're at it. What is VF1?
0.01060.
Cubic meters per kilogram. Plus the quality in state one is still 60%. They didn't give us VFG, did they? Okay, so VG is how much?
0.8857.
And VF we'll just subtract off. Notice that subtracting off VF is sort of a waste of time. Okay. Cubic meters per kilogram. Okay. So once someone, bless you, once someone has that, we'll write it down over here. But we realize we need one more property. We need the specific volume in state two, which is VG at 200 kilopascals, but we just used it. It's right here. It's 0.88578.
Not this VG is, it's all vapor, right?
I'm sorry?
It's all vapor.
It's all vapor at that point. That's why it's just VG. Good question. Guys, don't let me go too fast. I know what it's like to try and keep up. So if you have questions, slow me down or ask.
That one's,
0.53. 0.531?
0.532.
2? Okay. Cubic meters per kilogram. Okay, now the pressures are known, specific volumes are known, the mass in state one's are known. We haven't introduced any new unknowns. We've gotten rid of an unknown or added an equation. So, what happens? Well, let's rearrange this equation. One of the things they wanted to know was how much mass comes in, right? That was one of the questions. They didn't care about the mass in state two. So we probably don't want to eliminate the mass that comes in. Instead, let's just plug it in anywhere that we see an M2. We'll plug it in there, and we'll plug it in here. So the boundary work will be equal to P times, M2 is M1 plus the mass that comes in, multiplied by V2 less M1 V1. So there's our boundary work. We can plug it in over here as well. Mass in, enthalpy in, less, let's just go ahead and pull the boundary work equation over here, P multiplied by the quantity of mass 1 plus mass in, V2 less M1 V1. Okay, so that takes care of this piece. Equals, and instead of using M2, we're going to use this, M1 plus Mi. So the mass that comes in times U2 less M1 U1. And now we have a big math problem.
Yeah. But, we'll do that second.
We calculate mass in, that's right. All we have to do is rearrange it and solve it for mass in. We're done. I don't like rearranging and solving, throw it in Excel and use LOCIC for mass in. Another way to solve it. Everyone's looking at that equation like, can you expect us to do that?
I just think that, I mean, that's how you would do it. I'm sure that there's, more than one. I'm sure that every way you skin the cat's gonna take all those pieces,
That's right.
but you don't have to do it that way. I'm sure you could piece it together another way.
Well, the thought process is still pretty much the same. You still have to
Yeah.
have the same pieces. I don't think the energy balance is going to change.
Nope.
You don't have to do it in the order that I did it in. You could
Try to just
do it
get the
mass
pieces.
in. Yeah.
I try to just get the pieces of the puzzle that I was missing, and then I'll go home and
So
do
put
it.
together.
Yeah. If I try to think exactly the way you think, then it doesn't work, because I'm not you.
Right. Makes sense. Any questions on this problem? Did that answer your questions, Mr. Blackman? This is an unsteady problem. They're typically harder than the normal problem that we work. This one isn't really too bad.